Hi, in this video we're going to do introduction to Riemann sums. So when we're trying to approximate the area of a particular region that's enclosed by a curve, we use what's called Riemann sums. They're named that way after a German mathematician, Bernhard Riemann. So we recognize typically four types of sums that are most commonly used. That's left sum, right sum, midpoint sum, and the trapezoidal sum. We're going to use an example where our function is going to be f of x equals x squared plus 1, and the region is going to be bounded by the curve, the x-axis, and the lines x equals 1 and x equals 5. So when you deal with Riemann sums, you can use any number of subintervals, but typically it is given to you in problems you might be working on, and so we are going to use 4 subintervals of equal length. That means that each subinterval is going to be what? Well, we're going from 1 to 5, so it's going to be 5 minus 1 divided by how many we have? 4. So it's 4 divided by 4, so each subinterval is going to be 1 unit wide. Let's go ahead and take a look. So we're going to sketch a representation and approximate the area of the region including the left Riemann sum. So left Riemann sum means when we build our rectangles, they're going to be their left corner, upper left corner is going to sit on the curve. So right here from 1, we're going to go up here and we're going to go with a rectangle whose width is going to be 1, and here we sit on the upper left corner sits on the curve. Then we do the same thing here. So it's from 2 to 3. The upper left corner sits on the curve. Our third one is going to be here. Again, our upper left corner sits on the curve, and finally our fifth rectangle is going to be like this. So all we need to do now is find the area of each rectangle and add them together. So how are we going to do that? Well, we know that the width of each, to find the area of a rectangle, first of all, is going to be length times width, right? So in our case, the width is going to be the same. Width equals 1. And the length, which is, we're going to view it as the height, is going to be determined by the value of the function at that particular point. So like the height of the first rectangle is going to be determined by the value of the function at 1, because that's how far you go. The value for the length or the height of the second rectangle is going to be determined at 2. For the third one at 3, for the fourth one at 4. So the width of the first rectangle is 1 times the height, which is going to be f evaluated at 1, plus the width of the second rectangle is 1, plus the height evaluated at 2, plus the width of the third rectangle is also 1, times the height evaluated at 3, plus the width of the fourth rectangle times the height evaluated at 4. So it's going to give us 1 times 2 plus 1 times 5 plus 1 times 10 plus 1 times 17, and all that is going to equal 34. Okay, so that would be an approximation. This clearly is under approximation because we have all these gaps here, but it is an approximation, and that would be the answer here. So for our second example, we're going to do the same thing, but we want to use it, we're going to approximate the area of the same region, but we want to do it using the right Riemann sum. So when you use the right Riemann sum, you want the upper right corner of a rectangle to be on the curve. So I'm going to go this way because that's the right side of the interval from 1 to 2. So this one's going to be like this. The next one's going to go like that. The next one's going to be like this. And the next one's going to go all the way up here. Okay, so I hope you see the big difference here is that instead of the left corner sitting on the curve, the left corner of a rectangle, the upper left, we have the upper right corners sitting. So how does this change the problem? The width obviously remains the same, but the height, for the first rectangle, the height will be determined by the valued function at 2, because that's where the right corner is going to be. For the second one at 3, for the third one at 4, and for the fourth one at 5. Otherwise our setup is going to look identical. So we do what? The width times the value of that f of 2, which will determine the height of the first rectangle, plus the width of a rectangle times the value of 3, that determines the height of the second rectangle, plus 1 times f of 4, plus 1 times f of 5, right? So we're getting 1 times 5 plus 1 times 10 plus 1 times 17 plus 1 times 26, and all that is going to equal 58. See, there's quite a big disparity between that answer and the answer we got in example 1, because in this case it's an over approximation. We got all these things protruding, and that's why it's more than the actual area is. But again, that's an estimate, and that's our answer in this case. Okay, for our third example, we're going to use a midpoint sum. So midpoint sum means the middle of the interval of each interval is going to be where what's going to sit on the curve. So between 1 and 2, it's going to be at 1.5. So at 1.5, and that's what your first rectangle is going to look like, because the height of that is going to be determined of the value of the function at the middle of this interval, and that's the point that's going to sit on the curve. So for our next one, we're going to go at 2.5, and that's going to be our second rectangle. For the third one, it's going to be at 3.5, and it's going to be our third rectangle. And for the fourth one, it's going to be at 4.5, and it's the middle of each interval, and it's going to be our fourth rectangle. So just like the previous problem, the width is always going to be 1, but the value of the function, to find the height, the value of the function is going to be determined at the middle of each interval. So it's going to be 1 times, for the first one, it's going to be f of 1.5. For the second one, 1 times f of 2.5. For the third one, it's going to be 1 times the value of the function at 3.5. And for the fourth one, it's going to be 1 times the value of the function at 4.5. Okay? These are not too bad of values to do, but a calculator might be helpful. But I already know what they are. It's going to be 1.3.25 plus 1 times 7.25 plus 1 times 13.25 plus 1 times 21.25. After you add all this, it's going to be 45. So as far as over or under approximation, this one's hard to say. This is probably more it's probably closer, more accurate, when you try to compare it to the actual value. If you look at the graph, it's definitely higher than the under approximation and lower than the over approximation. So out of everything we've done so far, it's going to be the most accurate. Alright? And our last example is going to be a trapezoidal sum. So what you need to understand here is when you are looking at a trapezoid, your trapezoids are going to look like this. This is going to be the height, and this is going to be base 1, and this is going to be base 2. So you are going to build trapezoids now. So from 1 you're going to the curve, from 2 you're going to the curve, and then you connect them. Then you're going to this point, and you're going to connect them. Then you're going to this point, and you're going to connect them. And you're finally going to that point, and you're going to connect them. Okay, so these are 4 right trapezoids. The find the area of a trapezoid, you use the formula 1/2 times the height times base 1 plus base 2. So this one's going to have a lengthier setup, because for each of them, for each trapezoid, you're going to have to use this formula to set it up. So we're going to have to be very careful with our space here. So it's going to be 1/2. So it's going to be 1, it's going to be 1 times 1/2 times 1, which is the height, which in our case is the width of the interval, times base 1, which is going to be the value of the function evaluated at 1, so f of 1, plus base 2, which is the value of the function at f2. So that's for the first trapezoid. For the second trapezoid, it's going to be 1/2 times the height times. Now we're using these two, so the one base is going to be evaluated at f1, the other one is at f2 and f3. Plus, for our third one, I think you're beginning to see the picture. For the third one, we're going to have to find one base by evaluating the function at 3 and the second one at 4. So it's going to be f of 3 plus f of 4 plus, and for our fifth one, I think you see now the pattern is going to be 1/2 times 1 times f of 4 plus f of 5. Okay, so what would make sense here is we have 1/2 in front of each one, so we can factor it out. Because the width is the same, we can pretty much neglect it, but I'll write it here. And what's going to be left? It's going to be f of 1 plus f of 2 plus f of 2 plus f of 3 plus f of 3 plus f of 4 plus f of 4 plus f of 5. Right? So what's all this is going to be? So it's 1/2 times the f of 1 is 2, f of 2 is 5, f of 2 is 5 again, f of 3 is 10, f of 3 is 10 again, plus f of 4 is 17, plus also 17, and plus f of 5 is 26, and all this is going to end up giving you 46. Okay, and I hope this was helpful.